So this is the next concept. Now, the reason there's so many circles here, and if you notice, it looks very similar to what we just finished doing. However, what I've done now is I've actually put a circle on top of the Cartesian plane. So what's happening here is we call this circle the unit circle. Okay, so it's called, get my pen up where I want it to go. So this is called the unit circle. Now the reason we call it the unit circle is because its radius is 1 unit. Okay, so it's called the unit circle. So that means if the radius is 1 unit, from here to here is 1. So if I actually put it as that, so that would be the coordinate 1, 0. And that means that at the top here, I would have the coordinate 0, 1. Over here would be -1, 0. And finally, down at the bottom would be 0, -1. Now, what we're going to do here is something that is redefining the angles, how we think of them. Okay, so far we talked about coterminal angles, and I think you understood that, hopefully. So now what's going to happen is I'm going to start with my unit circle, and I'm actually going to make a right-angled triangle eventually. So I'm going to draw a line from the center of the circle to a point on the unit circle, so on its circumference. Okay, and that point, I don't know what that point is, so I'm going to call it point P, and I'm going to give it a coordinate x, y. Okay, because it will have an x coordinate and y coordinate. The next thing I'm going to do is I'm going to drop a perpendicular down from P so that it's perpendicular to the x-axis. So that's the next step that I'm going to do. So I will make it dotted and I will make it purple to match. So I'm going to take it and I'm going to drop a perpendicular down. So it's a perpendicular, so that means that this is a right angle. Now, I'm interested in this coordinate that's here, okay? Now, in comparison to the point P, I know the distance from the origin to that point has to be the same value as the coordinate of the x coordinate of point P. We all agree on that part, hopefully. So that will be our x value, okay? So this is obviously, this would be, if we actually wanted to put the coordinate, it would be x0, or the length here would be x. And also, if I go across here, I would know the distance along the y-axis. It's the same distance here of the dotted line that we dropped down. Okay, and it's going to have a coordinate of 0y. Okay, and that actually means that the distance here, okay, this vertical distance is y. I go up y units, so that means that this actually equals y. Now what I'm going to do is I'm going to define, remember theta starts at the initial arm and stops at the terminal arm. So here is my theta. Now, we know a lot of things about a right angle triangle. So we can talk about this as far as SOHCAHTOA goes. Now, one other thing I want to point out is we know the length from the origin to the point P is 1, and the reason it's 1 is because it's a unit circle that has radius of 1 unit. So the radius equals 1. Now, let's take a look at, for a minute, our sine ratio. Sine of theta we know is opposite over hypotenuse. Okay, so let's take a look at our triangle that we have here. Here's theta, so opposite of theta is y, and the hypotenuse is 1 unit. Now we would never keep something as y over 1, that's the same as y. So actually what we found here, is that sine theta actually equals y. And that's really, really important. Okay, that's important. And you'll see why when we get to these other circles. Now let's take a look at our cos. Cos we know, as soon as I get to go where I want it to go, get up there. Cos theta is adjacent over hypotenuse. So again, if I look at this unit circle and I look at this triangle, the adjacent side, this is opposite, and this hypotenuse is x. It's got the length of x, and it is over the hypotenuse, which is 1, which means that cos theta equals x. Again, very, very, very important. Now, the other one that we look at is also tan. And so let's take a look at tan. Tan of a theta equals, we know, opposite over adjacent. Now, if we look here, opposite is y over x. Now, also, let's take a look at if it's y over x, well, y was sine. So actually, tan is made up of sines over x's. So that's important too. It's actually got a special name. It's actually called the quotient identity. Not that we study the quotient identity in this course, but that's what it is. So those are 3 really important things that we've just discovered. Now, you're saying, okay, well, that's fine. You've got that. But what happens when I'm in a different quadrant? Well, I'm going to take that P, and this time I'm going to put the P over here somewhere. Okay, and it also will have an X and Y coordinate. And what happens with point P, and as soon as I draw, can I draw a straight line? Not too bad. Okay, so what happens is this is our theta this time, and you can see it's greater than 90 degrees. Now, I can create a right angle triangle here. Okay, I can actually drop a perpendicular from point P the same way as I did before. And this time, you'll notice what happens is this here is our length of our x, but this time it's going to be negative value. So it's going to be very similar to what we did up here, except we know that over here the x is negative. But what about the y? Well, the y in this coordinate is a positive value. Okay, so it's a positive value in that quadrant. Now the same is true. I can go down here and I can create the point P. And again, what happens to that point P down here is we know that it has a negative x value and a negative y value. Now, this is going to come important when we go to the next page, because if we're looking at an angle down here, and I have no idea what that is, it has to be between these two, say it's 250 degrees. If you took your calculator and found the cos of 250 degrees, you're going to get a negative number. If you take the sine of 250 degrees, you're going to get a negative number. And you'll see that when we, as I said, when we go over to the next page. Okay, so the same thing down here, but this time we're going to have a positive x, but our y is going to be negative. So what happens in all these quadrants is we can easily make right angle triangles. And these right angle triangles are almost like reflections into the different quadrants. Okay, so you could have the same right angle triangle in all 4 quadrants, and their x and y coordinates would be very similar, except sometimes they're going to be positive depending on what quadrant you're in, and sometimes they'll be negative depending on what quadrant you're in. Okay, so let's go to the next page. And this is what we call the cast rule. So actually what we're going to do is we're going to take our calculator and actually fill this in. Okay, so I've brought up the graphing calculator for us to do it. So let's, for instance, if I do sine of 60, if I do the cos of 60, and because it's graphing calculator, I can put all of them at one time, and then I'm going to do the tan of 60. If you notice what I'm interested in the numbers, but I'm also interested in whether they're positive or negative. So I'm going to put the first one as positive zero point 0.8, even though I should use 4 decimal places. That's just going to make our life, actually, it should be 0.87. The next one I'm going to put is positive zero point 0.5, and then 1.73. And so that's what I'm going to put here now. So up comes, so this one was positive 0.87. This one was positive zero point 0.5. And this one was positive 1.73. Okay, no surprise there. Let's take the calculator and do the next one. Okay, so now I've entered those, and you can see that I have this exact same numbers, except some of them are still positive, but some of them are negative. Okay, and so that's important to look at that. Okay, so I'm going to now copy those down. So this one was positive still. This one was negative zero point 0.5. And this one was negative 1.73. So that's making me think that maybe these have the same right angle triangles, but just in a different quadrant. Okay, now let's try it with 240. And again, you can see that we have the same numbers, except again, we have some different ones that are positive and negative. So this time, this is negative 0.87, negative 0.5, and you should remember tan equals is sine over cos, so this was positive 1.73. And finally, we're going to do the last quadrant, quadrant 4. Again, you can see we have the same numbers, and different ones are positive and negative. So this time we have, this one is negative 0.87. This one was positive 0.5, and this one was negative 1.73. So the reason we call this the cast rule is because it tells us that in certain quadrants, certain ones are positive and certain ones are negative. So in the first quadrant, all of them are positive. You can see all the ratios are positive. In the second quadrant, it's only the sign that is positive. In the third quadrant, you can see that it's only the tan that was positive. And finally, in the last one, it's only the cos that was positive. Okay, and so that's important for us. Now, actually, if I drew these angles on our axis that I just finished doing in the earlier part of the video, these would have the exact same right angle triangle created in all 4 quadrants. And that is why their ratio numbers are the same. And also that's why some of them are positive and negative. So I'm going to I'm actually going to start another video, and we're actually going to do some examples now, and then that will be it.